All right, so we've got AP 1, Unit 6 and 10. I'm going to combine those. Lesson A, which is just on Unit 6, Oscillations, Multiple Choice. Block attached to the lower end of a vertical spring oscillates up and down. If the spring obeys Hooke's law, means it's a normal spring like we've studied, no big deal. The period of oscillation depends on which of the following. So not to jump in all equation-y on you right away, but if we take a look at the equation for the period of a spring, so the period for a spring, this is one that you're given on your equation sheet, is 2 pi times the square root of, I believe, m over k. Verify that. The bigger it mass, the longer it should take, the bigger that is. So yes. So I don't remember the formula. I just remember the way things function and know which one of these goes where. So for a spring, the only things that matter are the mass that you attach to it and the spring constant. That's it. The amplitude does not come into play. The amplitude would be if you attach the spring and normally it hangs, to here, to this level. The amplitude would be, let's say you pull it down this far and let it go. Or that would be an amplitude of whatever this distance is. Maybe you only pull it down this far. That's a smaller amplitude. That doesn't actually affect the period. It will still go back and forth in the same amount of time. So all that matters is the mass of the block and the force constant. So 1 and 3. Pendulum, consisting of a sphere suspended from a light string, is oscillating at a small angle. Small angle is a technicality. Don't worry about it too much with respect to the vertical. The sphere is then replaced with a new sphere of the same size but greater density, so more mass in other words, and is set into oscillation at the same angle. How do the period, maximum kinetic energy, and maximum acceleration of the new pendulum compare to those of the original pendulum? Okay, so the period is unchanged by the mass because period of a pendulum is 2 pi, and let's see, L over G. And the length is all that matters, not the mass. So by changing the mass and not changing the length, then I'm down to the period's the same. It's one of these two. So I'm down to a 50-50 guess even if I'm stuck. Now, maximum kinetic energy, well, that depends. They pull it back the same angle. So it has the same height difference. So it has the same, well, it has the same height difference, but the mass is different. And both potential and kinetic energy depend on mass. So the total kinetic energy should be more at the bottom because it's got more mass. Just ask yourself, getting hit with it when it's a bowling ball as opposed to a tennis ball. There's definitely more energy involved in the bowling ball. So I would say larger kinetic energy. Acceleration is going to be the same because how much speed it picks up is independent of mass. Because the mgh here equals the 1/2 mv squared down here. The m's would cancel if you set them equal to each other. So that would be d. Pendulum has a length L and a bob of mass m. Which of the following is true of the linear momentum of the bob as it swings from the highest to the lowest point? It remains constant because momentum is always conserved. Only if all the forces are internal. And since they're not talking about the Earth bob system, they're talking about just the bob. The Earth, gravity of the Earth is an external force, so momentum would not be conserved here. It increases in magnitude and changes direction. I'm not disliking that answer. It definitely gets to be more as it falls downward. It picks up speed. And momentum is mv, and so v would get larger as the pendulum goes from here to here. It does increase in speed. Certainly the direction is changing. It's going this way, and then it's going straight across, and so forth. So I kind of like B. Let's look at the others. It decreases in magnitude. No, it does not decrease in magnitude. Highest point is low velocity. Lowest point is high velocity. So yeah. Angular, we'll convert it into angular momentum. Actually, it has both at the same time. You can look at it just two different ways. It's converted to kinetic energy. What's converted in? The linear momentum is turned into energy. That's not really a thing. like momentum is momentum and energy is energy, and you can't turn one into the other. So we're going to go with B. Simple pendulum of a mass hanging on a spring, both have and a mass hanging on a spring. Got it. There's two of them. Both have a period of 1 second when set into small oscillatory motion on Earth. They're taken to planet X, which has the same diameter as Earth, but twice the mass. That's twice the gravity then. That's G, right? So or G on Earth is big G, mass of Earth, divided by the radius of the Earth squared. On our new planet, G new, or planet X, I should say, the G on X is going to be 2 big G mass Earth, has the same radius of Earth. So we doubled G, went from 9.8 to 19.6. Which of the following statements is true about the periods of the two objects on planet X compared to their periods on Earth? All right, so if we remember, the period for a pendulum, 2 pi L over G, does depend on G. But the period for a spring is 2 pi square root M over K. It does not depend on G. So this would still be 1 second. The spring would be, but doubling G is going to reduce this to this, and then you still have the square root involved. So doubling G is going to produce a square root of 2. So this is going to be smaller by dividing by square root of 2. It's going to be smaller, so less period. So the period of the mass on the spring is shorter. Now, the period of the pendulum is shorter. That of the spring is the same. Yes, that's the one we want. They're not both the same. Changing G does affect the pendulum, but not the spring. Simple pendulum consisting of a small object of mass m attached to a string of length L has a period of T. A pendulum with which of the following combinations of mass and string length will also have a period of T? So once again, mass doesn't matter for a pendulum, just the length. So in order for it to have the same period, it better have the same length. So I'm assuming 4L string length is a fourth. 2L. I'm assuming this is 1L, right? It's got to be A. Yes, because it has to be the same length. Has to be the same length. Mass doesn't matter. Simple pendulum is used to determine the acceleration due to gravity on the surface of a planet. Pendulum has a length of 2 meters and its period is measured to be 2 seconds. The value of G. So, period for a pendulum is 2 pi square root of the length of the pendulum, which is 2 meters, over G. So we're solving this for G. This here is the 2 seconds. So I have 2 equals 2 pi square root of 2m over, well, 2 meters, 2 over G. Well, first of all, I can divide both sides by 2, so I get 1 equals pi square root of 2 over G. Let's square both sides. So 1 equals pi squared times 2 over G. And now we're solving for G, so we'll just put it up, multiply both sides by G. G is pi squared times 2, 2 pi squared. All right, so we'll punch that out real quick. He says, here we go. So pi squared times 2 is 19.7, so about 20 meters per second squared is G. And just double checking my answers, that is correct. All right. An object is in simple harmonic motion. Of the following quantities related to the object, which set of three can have maximum magnitudes at the same instant of time. I think probably the best one to think about for me is a mass on a spring. So horizontally. So if here's your equilibrium position, here's the mass when it's in the middle, here it is completely compressed, and here it is completely stretched out with this distance being the same as this one if it doesn't look it. That would be your amplitude. All right, so when it's out here, what do we know? We know velocity is 0, acceleration is a maximum, net force is a maximum, displacement is a maximum. All those are true out here. The velocity is stopped though. So A is your largest displacement. At this point, the spring is pulling on it as hard as it can. So net force is a maximum, which means acceleration has to be a maximum, even though it's not moving. Let's see what we have. All right, now we got kinetic energy. Now, kinetic energy here is 0, but potential energy, spring potential energy, is at a maximum. Your spring is as stretched as it's going to be, or compressed if you're over here. So this is true of the exterior part. In here, you have velocity as a maximum, kinetic energy as a maximum. Everything else is at its minimum, is at 0. Acceleration 0, net force is 0, displacement 0, potential energy 0. But they want to know which ones are maximum. So I would go with, it is possible for acceleration at the end, potential energy, and displacement to all be maximums at one of the ends, either this end or this end. So I would go with 1, 3, and 5 if it's an option. There we go. An object moves up and down the y-axis with an acceleration given as a function of time by that, okay, where A and omega, right? I should know this. I'm doing this during the summer. My brain's a little turned off. Are constants. So the angular speed is constant, so to speak, and alpha is constant. Okay. What's the period of the motion? All right. So period is going to be based on this. And I believe it's omega divided by 2 pi. It's the other way around. I'm looking it up now as I speak. I know 2 pi, you do something with 2 pi. And going back to my recollection, I believe, and I know it involves a division. It's either this or it was this, 2 pi divided by omega, and it turns out to be this one, if I'm looking at my answers correctly. D is 8, yes. So it's this right here. So the rule is, whatever the coefficient is next to time in this case, it's going to be that divided into 2 pi, the length of one period. An object of mass m attached to a spring with a spring constant k oscillates amplitude a. Assuming air resistance and the mass of the spring are negligible, which of the following changes alone will cause the period of the oscillation to increase? So the period of oscillation for a spring is 2 pi square root m over k. So if we want this to be larger, we're either going to make the mass larger or k smaller. Those are our options. Amplitude won't make any difference whatsoever. Increasing m would make the period bigger. Greater k would not. That would make a smaller period, right? If you make this bigger, that makes this smaller because it's dividing in. So really just one only. Sphere of mass m1 is attached to a spring and is displaced downward from its equilibrium position as shown above and released from rest. The sphere of mass m2 is suspended from a string length of L and displaced the distance shown and released so that it swings in a simple pendulum of small amplitude. Assume that both spheres undergo simple harmonic motion. If both spheres have the same period, which of the following is an expression for the spring constant. So they have the same period. That means 2 pi m1 over k is equal to the period of the pendulum, which is 2 pi square root m2, not m2, m doesn't matter, L over G. And they want to know the spring constant. They want to solve for that. Well, the good news is that divides out. We can square both sides. So m1 over k equals L over G, and they want k. So let's flip everything. K over m1 equals G over L. Multiply both sides by m1. K is G m1 over L. So that's what I'm looking for. G m1 over L. I'm going with E for number 10, and I would be correct. So we set them equal, and we solve for what they want, which is K. This is the period of the spring, this is the period of the pendulum, and then we do the algebra to get K by itself. All right, here endeth the first video. We'll do the numbers 11 through 19 in a second video.